Thank you very much. I'll give a brief introduction to GPS flash timing. I've only got 30 minutes, so it is going to be a fairly light presentation. There's a lot more detail behind this, so if anyone wants to learn more or discuss more, then please contact me afterwards. So why GPS timing? We have a need for accurate timing, and GPS 1 pulse per second flashes can give that because it syncs to GPS satellite time and to UTC. The main advantage is that it's usable with any type of camera, be it analog or digital, so we're not tied to a particular technology. It does give a simpler overall setup than the analog VTI. The picture there is my old setup. Sorry, I just need to get rid of this. Get out of the way. That's my old setup on a Celestron C6 with a Kiwi VTI camera, cables and power supplies galore. Most of those cables disappear, and with it being digital, you can use your favorite acquisition or telescope control software. It is also future-proof in the sense that it doesn't depend on ongoing availability of VTIs, doesn't use legacy analog hardware, and it's not contingent on a single developer to support it. It's also cheaper and more accessible, and for those of you in the room who have looked at occultations and thought, how the hell am I going to do this? GPS flash timing gives you an opportunity to actually use all of your existing camera gear and just add a timing component without any major modifications or any expensive new setup. There are a range of GPS flash timing methods. They're very clear in my head. They're probably not very clear in your head, so I'll just give you an overview. The two main methods, there's a set of timing methods that I've called SMART. So this is the ones you're probably most familiar with. These use a dedicated GPS flash module that logs the GPS timestamps, so you can use them later in your analysis. The ARTS flashes, the Chrono Flash, and the new IOTA GPS flash timer that's under production are these types. So those are completely standalone units and they record their own time. The method that, for want of a better word, I've used dumb, this just uses a GPS flash. It does not record the timestamps in the GPS unit at all. So the GPS has no knowledge of what the time actually is. This is used in Japan with their timing system, the main timing system that they use. It's also used by an observer, Pierre Lecam, who has published some work on this, but that method's probably not very familiar to most of you. When I went to look at GPS flash timing methods, I reviewed all of these, and I decided that the method of Lecam was most appropriate to my situation, given that the instructions are not in Japanese. So I'm going to be demonstrating the method of Lecam using a dumb GPS flasher. And along the way, I'll also discuss some of the issues that affect all of the GPS flash timing systems that need to be considered to give the most accurate timing. So to get started, you actually need a GPS flash source. This one will start ticking away. This unit, the little USB stick, this part of it, that's around about $12 from Amazon. It's the same model that's used in Japan, so it's been well tested. It's just a very, very simple GPS device, and it has a LED that flashes once every second. And you can power it from a USB cable or, as I do, from a USB stick, and it can just sit in your pocket. It only requires a very, very minor modification. You just pop the case open with a craft knife, you just gently scrape on the red LED until it's destroyed, and it's done. So there's no DIY build, there's no soldering, there's no programming, there's no 3D printing. Pretty much anyone could pick up one of these units and use it, and it is very cheap. There are other GPS sources. If you're prepared to do some very basic soldering, which I was, I've built a basic flasher using this GPS flash module, which is for an Arduino Shield. Just had to wire in an LED, which I actually used one of my 12-volt power connectors because it's got an LED into it, and soldered that on. So I've built this in, and it's now sitting on my telescope. And as soon as it's plugged in, it starts flashing. There's also other units such as this Global Sat, which is a USB powered unit. I haven't tested this, but I'm quite interested because this might actually give GPS time to the PC and a flash source. And both of these have a separate antenna, so you get a faster satellite acquisition and better stability. So with the dumb systems, they do not log the time. So you need to somehow find out where the nearest UTC second is. So to do that, you have to discipline the system time. You can use NTP, you can use a GPS receiver with BKT time sync or MENA time 2. There's a few different ways of doing this. The main thing is that you need to, so one of the criticisms of NTP is that you need to have an internet connection. You can do this timing using a 4G or 5G hotspot. And you can also do this timing using the GPS USB receiver as the time source to discipline the PC clock. The main thing is that the PC time must be accurate to well less than a second so that you can reliably identify the nearest UTC second. And that's absolutely critical to this method. Timing accuracy on your PC of roughly 100 milliseconds is fine. Mine generally runs at between about 5 and 10 milliseconds from UTC according to NTP. And you must record the timestamp frames, because what this method does is it measures the camera delay and then you adjust the timestamps on the frames. So you have to have the timestamps. I use ADV format in SharpCap, which is now available in the upcoming release. CF format or FITS is okay. Could use AVI if you have the on-screen timestamps, but I wouldn't recommend it. So the main thing is that you need to get the PC time disciplined, and that's a fairly easy process using that software. I won't go into those details today. It's out of scope for what we're looking at. So to actually flash tag the observation, it's a fairly simple process. I usually just do a 3-minute recording, and all I do is I just hold the GPS flash unit in front of the scope tube, and that puts the flashes down the tube and they get recorded. So I do 3 minutes, so I've got enough time to get up from my seat, put those recordings in and out. You do need to position the flasher so you get even illumination. It's absolutely critical you get no saturation because that will destroy the timing measurements. So I usually aim for 30 to 50% on the histogram. And with a bit of practice, I've got my setup dialed in. So you can alter the angle, you can alter the position a bit. Sometimes you might need to put a bit of tape over it if your LED is too bright or whatever. You just need to experiment to find the right illumination for you. For this method, this may not make sense to you, but the duration of this flash is 100 milliseconds. So the flash will occur over 2 or more frames to do a measurement. I recommend that you use these kinds of settings so that the flash time doesn't stay in sync. Because if you have an exposure time that is longer than the flash time, you could end up with the flash occurring completely within 1 frame, never crossing between 2 frames, and then you can't do a time measurement. So this is really the only restriction. It's not really a serious restriction. It's just have to be careful on the exposure times that you set. And I usually do a series of about 10 flashes. That means the position of the flashes will cycle with respect each frame start, and I should have some usable flashes within the time. And of course, it's handheld, so your illumination will vary, and sometimes you won't get it in the right place. Once you've got the recording done with the flashes, then I use Tango to do light curve reduction, and then I do analysis to measure the offset. And principally, you could use any light reduction software. It doesn't really matter. You do need to set the measurement aperture in the right place, and this does depend on your camera and your mount as to where you should put that aperture, and it's one of the things I'll discuss later. It's something I don't think has been well understood about GPS flash timing. Do you need to use aperture photometry? None of the fancy methods, otherwise you won't get an analyzable result. And in Tangra, it does have an option for entering an acquisition delay. You'll see this once I go through the process. You need to set that to 0 so you're not making any adjustments to the time when you're measuring the time in offsets. So you generate the light curve with your target star, and will record the flashes, and you then save it to the CSV. To do this, I'm using an Excel calculator which has been modified by the calculator that Pierre Lecam published. This automates and streamlines the calculation, and it gives a visual selection aid for the data processing, which makes the whole process quite easy. I've built in some basic error checking just to help people out. I know what I'm doing, but if anyone else uses it, it's a useful guide. So what it does is it calculates the acquisition delays and also the corrected UTC for the flashed frames. And it also interpolates this to the event time. And that's an important process that I'll take you through as we go through. Okay, I will now flip screens to show you how the delay calculator works. So I've set it up in Excel. This is actually in Google Sheets, so it should be usable by anyone with an internet connection. This is the main screen with the control. Here is an example of the light curve. You can see the peaks here before the event. These are the flashes. The event occurs in here. And then these are the post-event flashes. And you can see their intensity varies, and that's a result of hand handling the GPS flasher. Here I must have just moved it a bit and the signal went a little bit wonky. So we need to select the events that we're going to use. The light curve is just copied in bulk, just to control all to select the whole thing, paste it in. Then it's available on the main screen here. And what we need to do is identify a period within the light curve for the first set of flashes, and they occur at roughly frame 100. So we go to the flash one and then let's the screen, type in frame 100, it looks up the data, and then it displays a series of flashes. You can see these are reasonably well spaced. Some of them have a slightly different shape because of the relative timing. This does the flash timing on the background. I usually put the measurement aperture on the target star. So this has actually got the target star in it. So we're just wanting you to use the background. What I need to do is you can see here, we've got a background level of around about 100,000 ADU. So we want to set a level where we can filter those out and subtract them from that background. So this, I'll just put in a level of about 110,000. So what this does now is it subtracts that, calculates an average background for those where the flash events occur, and we get an average background calculation. And then the process to do one more thing. We need to set the exposure time. If you put the wrong exposure time, it says you're probably wrong, so please sort it out. Sorry. And in this case, we've got a nominal 80 millisecond exposure. So what we need to do now is just tag the events that we want to be analyzed. So here you just enter 1, 1, 1. This just tags these 3 events here. You can see there's a series of zeros. What that does is it then calculates how much of the, how many milliseconds the flash pulse was in the first frame, and there was 1.5 milliseconds in the first frame. And that can sometimes be a little bit unfortunate, because if you're trying to measure roughly 1% of the light in one frame, you're probably not going to get a very good signal to noise ratio. So in this one, I'd probably go to here, where the 100 millisecond pulse occurs over 2 adjacent frames, and they're sort of roughly equal in level. Put those 2 in, and then it calculates an average acquisition delay of 12 milliseconds. And as you go through, you can go do a few other events, and you'll see you will get a slightly different time for each event. This is a consequence of the signal to noise ratio in your observation, and that obviously was the wrong one to do, so I will just back that one out. Sorry, I must have left what have I done here? I left the 0 in the wrong place. I didn't null it out. So we get 11.2, 11.6, 12.2. That gives you some idea of how accurate this might be. Okay, so once that's done, we then have an acquisition delay that is calculated, the original timestamp for that frame, the correction applied, and the calculation there of the acquisition delay. Then we just repeat that process for the second frame. So for the post-event delays, they occur at around about frame 1900. 1900 in there. Background still about the same. We see it then, you can see obviously where these events are occurring. I'll probably want to go for one of these ones at about 1930 or so. So I'll just go down to here and try this one. And that's given me a delay of 12.7 milliseconds. So that's calculated the delay for some of the pre and post event flashes. Now what we need to do is actually calculate what the acquisition delay is at the time of the event, because things can drift and move. And I'll be discussing that a little bit later. So there's a little tool here that helps to identify it. So identify the frame for where the event occurs. That's roughly frame, where are we? About frame 1000. And what we do is we just tinker with this until the frame lines up with the red spike. And then this time now will be calculated at 70.41 seconds after the first flash, and that interpolates these delays to the event time. And as you can see, that event is slightly different. There can be sources of timing drift with the GPS flash timing, and this interpolation helps to correct for that, either partially or fully. So once that's done, that will be the acquisition delay that I've calculated for this particular event at this event time. So that's the work of the GPS flash timing done. Then it becomes a matter of doing the normal light curve reduction process. And in Tangra, I'd go and repeat the light curve reduction with a subset of the data that doesn't have the GPS flashes, so it doesn't end up in the light curve, which could cause people to question my sanity in posting that light curve. And this is the screen that pops up in Tangra, and I'll go through and enter the delay and as an acquisition delay. Sometimes the delay can be negative depending on your PC time offset. And if you do that, you then have to actually put it in as a reference time offset. So you do have to be a bit careful about how you put this through. My preference is to put these delays into the light curve. You can, I believe, add these delays into IOTA. I've never trusted myself to try and do it. I prefer this to be done before it goes to any further analysis. It just reduces the chance for error. The UTC times that we have, in principle, you could use these times as timestamps for Peyote, because Peyote can allow you to use GPS flash timing. But at this stage, this method of flash time, it isn't usable directly by Peyote. I've had a few conversations with Bob Anderson, and maybe at some point it might be possible to get this in there. Okay, so once we've got that, we've got a corrected light curve, and that gives the correct times for that. Now, I know one of the issues with timing is we have to make sure that it's reliable and accurate. So as far as the reliability goes, we want to know if something has gone wrong. So here's a few hints and tips in here. One of the things is to keep an eye on your PC time. If you use an NTP, it does give a report that you can look up to see what your NTP time offset is. And this is showing an offset of my PC time of a few milliseconds to UTC. And the other main thing is just to, use your common sense. I usually have an offset of about 10 to 20 milliseconds. If it's much higher or lower than that, then maybe I've got a problem. And that's how I actually identified that there was an issue with sharp cap change in their reference timestamps, because my acquisition delays went a bit haywire. As far as the physical hardware goes, as long as the GPS unit is flashing, then you've got a PPS signal. You don't have to wait 12 minutes for that PPS to be reliable. If your GPS is stopping and starting, then you need to be a little bit careful, because in that process of stopping and starting, sometimes it can get out of sync. If all else fails, you've got your PC time disciplined, so you could actually report an NTP time if you know your camera acquisition delays. So the $100 question, I suppose, how accurate is this? The real world signal to noise ratio has star background and other things, so you will get a lower accuracy than if you doing by bench tests. So just be aware of that. In principle, you could cover your telescope, do the GPS flashes, and that will reduce the background noise and improve your timing, but it is a lot less convenient to do that. I have got a paper in preparation with the Journal of Occultation Astronomy, so I'm not going to reveal anything about that until there's been some form of peer review on that. But I think it's accurate enough when it is done properly with accuracies of a few or low milliseconds are possible. Now, done properly is the key thing. In the process of using GPS timing, flash timing, I've come across a range of issues which I don't think have been well understood by the community, and I don't think anybody's actually fully taking care of all of these. The main issues to be aware of are drop frames, line delays, and intrinsic with rolling shutter cameras. And for this method, where I'm actually using the adjusted PC timestamps, drift in the PC time. So drop frames, if your exposure is too short for your camera's acquisition system to handle, you'll drop frames, and the effect will depend on how the timestamps are allocated. I've been told by Bob Anderson that Peyote assumes that there are no drop frames. it calculates and populates its timestamps. So if you do have drop frames and you don't take care of them, you could get a 1 frame timing area per drop frame, depending on when that drop frame occurs. The method I use when I'm applying the delay correction to each timestamp for each individual frame, the drop frames don't affect the timing of an individual valid frame. So the method I use is reasonably safe against drop frames. So you do have to check for drop frames and be careful of them. And if you are affected, do try and fix them up. One really helpful thing to do is to make sure you're using a time-stamped video format or a still format so you can actually detect if you've got drop frames. Big question, global versus rolling shutter. Global shutter cameras are better because they don't have these line delays. The rolling shutter are much more common and much cheaper. The rolling shutter camera reads line by line. There are delays between every single line as it reads out, and that can range up to about 10 to 20 milliseconds from top to bottom of the frame, and that's entirely dependent on the camera and your region of interest. The measured time will drift if your star drifts across the field in the Y direction, and how your star drifts in the Y direction will depend on your mount. Some will drift in a consistent direction and some won't. So that needs to be taken care of. I won't go into too much detail about this, but the two main methods are measure at the same Y line as your target star. Sorry, I'll just go back. One is to fix a measurement aperture at the same line as the target star at the event. That's a bit of a pain in the ass to do. So what I do personally is I measure the tracked star, and then I interpolate as I had in that Excel spreadsheet to the event time. You could, in principle, measure the delay per line and find out where the star is and do the calculations and corrections. That's considerably more complex to do, but it's technically possible. In a nutshell, because I've written pages and pages and stuff of this in my sort of documentation, depending on what your mount is, there's various things that you should or shouldn't do. If you have a guided mount, then you're in good shape. Pre-point mounts will drift consistently in the Y direction. Interpolation will fix them. If you align your sensor on an EQ mount, it will drift in the right direction in the right way, or not drift in Y at all, or at least not much. But if you have an alt-az mount or an unaligned EQ mount sensor, then you may have some issues, and that could introduce some minor errors into the timing. So it's best to take care of those if you can. PC time drift, because the times aren't logged, we're relying on the PC time for the base time for the frame and then correcting it for the GPS time flash. Your PC time will usually drift a bit, and it can drift enough during the time of an observation to move a little bit. That will generally be slow, and it will usually be linear. Newer PCs will tend to drift less, which is good news. Your older PCs tend to drift more. You do need to understand how much drift you have, so that's something to check with your setup so you understand how much time at drift there might be. And interpolation to the event frame and time will also correct for a linear time drift. So my good practice recommendations in a nutshell, there's quite a lot more detail behind this. Use pre and post event flashes, measure and track the target star at or fix it at the Y position of the event, the horizontal position of the event, and interpolate to the event time. And that will largely correct or fully correct rolling shutter line drift and PC time drift, with a few considerations about the mount. But by doing this, you'll get the most accurate times that are possible with GPS flash timing. So wrapping up, you can get accurate times for occultations with GPS flash timing. It can be as simple as a $12 unit and a craft knife to get yourself set up. It can be used to measure your PC time offsets for observations. You can also measure your camera acquisition delays for NTP timing. It's not as accurate as a sexta system, but for many purposes, it will be accurate enough to do those kinds of calculations. You do need to set up your PC carefully so you get reliable PC times, follow correct procedures and processes, and understand how your equipment is working so you can make the right decisions so that you can actually adopt the right procedures and protocols. And my opinion is it's time for us to actually explore this fully so that we can adopt some proper guidelines by IOTA and update some of our observation practice materials. Right, thank you.
Thank you for that, Michael. Very impressive. I'm going to have to go and watch the video again just to catch some of it. Questions from the room? Any questions online? No online questions. Microphone, Joe.
It's really more for Murray. What would be good is if we could get the direct Zoom link to that video so we can view it in high definition. Sometimes once they're translated to YouTube, because there was a lot of very fine text in the some of the screenshots.
We will have the PowerPoints as PDFs, so the read bit will be there. The video is more for what, Michael's words, or
yeah. Okay. Thanks.
I do have a question. I was wondering why you're not using several of the time pips at the beginning and say the end, rather than just picking one out and averaging over several.
I could do it. It takes more effort to do. I do have a Python script that will run through an entire light curve file and calculate the delays for every single pulse that's in there. That would give a slightly better result. The kind of variation you saw of sort of roughly 1 millisecond between each event is probably reasonably typical of my setup. For most of my observations, a variation of 1 or 2 milliseconds for an 80 millisecond or 160 millisecond exposure is, in my opinion, not significant. So yes, it could be done better than this method, but for most of my purposes, I believe it's good enough. Definitely room for improvement if we want to put the effort into those processes.
So, quick question from me, Michael. The GPS device that you're looking at there is quite a specific one. How specific does that need to be? I mean, I don't know how many of these sorts of devices have a 1 PPS LED on them.
Yeah, well, this one I don't know. Try and get it close enough to the camera. It says they're U-Blocks 7. U-Blocks is one of the main manufacturers of GPS receiver circuits. They have a U-Block 6, 7, and 8 series, and my understanding is they all do the same thing, which is the PPS on the UTC second to within a few nanoseconds and 100 millisecond pulse width. I use this one because they'd used it in Japan. They obviously trusted it and used it. I did my own tests against the Kiwi VTI to see that the flash occurred exactly on the UTC second, and it does to within one millisecond. I've also done video recordings at 1,000 frames a second to test the length. So it would pay if you are using another model to at least do some basic tests on that to make sure it's the right one. But this model is one that I'm confident does what I think it does. The one that I built for myself, I also repeated those tests. So there are some basic tests you can do yourself to verify. If you want to be completely sure, it's probably best to send it to someone who has a VTI or something like that can do it. But yeah, these are pretty ubiquitous electronic components.
Have you actually tried to compare with the QHY 174 by any chance?
If someone sends me one, I will. Anyone could do the test. You just have to get one of these with a craft knife and do it. If anyone wants to try it, I can give you some help to do that test. If someone wants to give me a QHY 174, I'll be very happy. I have done tests against the Kiwi video time inserter with a Waytech camera, and the times line up to the time resolution of that camera under ideal conditions. So I have done tests like that for that JOA paper that I'm in preparation. That's in preparation.
When you say destroy the red power, do you mean what actually physically destroy it, or do you cut it out?
You just destroy it. You just scrape it with a craft knife down to the circuit board, and it's gone. Or use snips or something. It's on a surface mount, so just a little bit of scraping. It takes maybe 5 minutes to do. Although I'd probably recommend you buy 2 units just in case you do destroy one of them in the process. But it's very easy. The case just pops open and it clips back again. So it's very easy to do. No tools apart from a screwdriver or a craft knife required.
Thanks.
One more.
When might you expect your paper to be released publicly?
It needs to go to review. It's probably going to be a couple of months on that. That one's about the time inaccuracy. So my assessment of the time inaccuracy in real world use. The actual documentation and calculator I can make available sooner than that. I just would appreciate some review before it goes fully into the wild.
Very good. All good. Thank you. Thank you for that, Michael. That's just food for thought there. Yeah, absolutely. And for all the new observers coming in with various ZWO and QHY non-GPS cameras, this is your ticket to ride.
Yep, sure is.